Anyone gets the problem of just looking at a star and trying to see if there's a planet next to it?
Contrast.
Contrast, yeah. If there was a mosquito buzzing by this car's headlights here, you wouldn't be able to see it. You'd be looking there, you wouldn't be able to see it. And that's the same issue with planets. Often, if you look at a star, your telescopes are totally swamped by the brightness of the star. And you can't make out any little planets next to it, like our little chia seed that I had earlier. Okay.
I couldn't make out the chia seed.
Yeah, exactly. That's a good demo. I wasn't even bright. I have a flashlight here that would really blind the chia seed. Okay. So there are people who are trying to figure out ways to remove the light of stars. So I used this as the sun earlier. So if the sun was really bright, one way you could maybe see the chia seed next to it would be to block the sun's light. And we actually had an astronomical example of that very recently.
Yeah.
Good old solar eclipse. How many people saw the totality? I didn't, unfortunately. I just saw the 90% here. A little cold, a little dark. So an eclipse is actually a good example of something called coronagraphs. And these are technological telescopes that scientists create to remove the light from the sun. They're very, very difficult to make because you need to have the telescope and the coronagraph. So corona means crime, as in coronavirus. And you need to have it very well engineered just to block out the light of the sun or the star. And then you need to be able to resolve the little planet next to it. And the moon does this much better than us. Whenever the moon blocks the sun, you can see these tiny little prominences, they're called, reaching out from the sun. You can see the corona of the sun very well. But the sun's very close, so it's much easier to block out its light. Whenever we look at stars that are very far away, there have been some successful detections of planets. This is my favorite one. This is HR 8799. Most astronomers know it by name, or at least planetary astronomers. And in the middle, we have our eclipse. We have the coronagraph that has plucked out the light of the star and removed it with a lot of complicated data analysis that I don't understand. And you've got this black hole here, and we have a planet, we have a planet, we have a planet, and this thing here contested, but probably a planet as well. And this has been observed since 2009, and we have got a movie of another planetary system moving over years. So here's the years ticking forward. This planetary system has actually been seen moving in orbit around its star. Aristotle would not be happy about that. Okay. The issue, though, the scale. So 20 AU. AU is that distance between the sun and the earth that I showed you earlier. That's the distance between the earth and the sun, and this is 20 of them. So on this scale, the earth would be removed from view. We would not be able to see Earth if it was orbiting the star. We wouldn't even be able to see Jupiter, which is 5 times further away. So these planets are ridiculously distant. This one is probably further than Pluto, and then this one is much further than Pluto, and then this one's much further than Pluto. They're also very big. They're like twice the size of Jupiter. So this method is spectacular when it works. Did you have a question?
Yeah, does that mean the star is also ridiculously bigger than the sun?
That's a good question. I don't think this one is too much bigger, maybe twice. But there is a general scaling between star size and planet size. I'm not sure about this one. Jason Wine actually was a colleague of mine for a while as well. He made this image. He loves making videos. So this works when it works. And it works when you've got big things far away from the star. Just like if the headlight of the car, maybe I had a very bright flashlight that I was near the car with. You might be able to see it if it was really, really bright. And the bigger the planet, generally the brighter it is. The problem is, as of yet, there is no way we would be able to use this to detect anything like the Earth. We can only detect things that are far away, which is really interesting. It's amazing to see these planets and to find them and study them. but if you're interested in finding life, they're not that good. We gotta carry on. And the first method of detecting planets that was actually successful is something called radial velocity. And this employs the Doppler effect, which some of you may have heard of, where a classic example is an ambulance goes by, it's high-pitched when it's coming towards you and low-pitched when it goes away from you. Right? The kids love it when I imitate that. And what that's doing is when the ambulance is coming towards you, the sound waves are compressed, and when it's going away from you, the sound waves are stretched. Compressed light, in the case of a star, looks blue, and stretched light looks red. So this flashlight, if I were to move it towards you quickly enough, it would look blue. Further away, it would look red. Yes, it didn't mix them. Okay. And this happens in, oh, I thought that was a movie, there we go. This happens in stars because we often think about planets as orbiting stars that are stationary, but really, they're always dancing around each other. And I have, I'm going to try not to blind anyone by doing this. So I have a star, and I have a planet, the ping pong ball. So you can have a planet orbiting in a big circle, but the star makes a little circle on the wall. You can really see that. Okay, so it's making a circle. And even though you can't see the planet, you can see the star wobbling. Really what's happening though is it's the other way around. It's moving towards you and away from you. That's what you see because you see the of the light, okay? Blue, red, blue, red, blue, red. And from that oscillation, you can tell there's a planet. There could also be another star there, so you need to be careful that everything matches up correctly. And in fact, this was used to detect stars by Doppler himself, who the effect is named after. It was first used for looking at stars that orbit each other. But it's just as useful for looking at planets. And people who were interested in looking for planets around other stars had a very long time to wait, because this only found the first planet in 1995, when I was 4. I was celebrating. Making a rocket ship out of Lego or something. Okay, and it has been very successful. And one of the more recent findings from it is Proxima Centauri. That's the nearest star to us. That's the one that's in Miami. If we use the scale from earlier. The nearest star to us has recently, within the last 5 years or so, been found to host a planet, Proxima Centauri b, which is in the habitable zone, which you might recall means if we grabbed Earth and put it there, it would have water on the surface. The issue is Proxima Centauri b is nothing like the Sun. It's a tiny star called a red dwarf, and it's unclear how things translate whenever you look at a planet around a different star. But still, its temperature would be right to have water on the surface, which is kind of exciting to me that even the closest star has a potentially habitable planet on it, or at least could have water on it. Okay. The problem is, if we want to find an Earth around a sun, like a sun-like star, this is a tiny star. Tiny stars get shaken around a lot more by their planets than big stars. Big stars like our sun, if we were to have our chia seed, the Earth, causing the sun to shake backwards and forwards towards you, you're basically detecting it moving. You're detecting a gigantic thing moving at some speed and making it look bluer and redder. And the Earth is so puny that that speed that the sun would be moving towards and away from you at is about 0.2 miles per hour, which is about this. Yeah.
So I can assume that the other planets kind of, some of them pull on the sun more, right? So if you find kind of this thing, how do you know it's one planet in the habitable zone instead of two planets that are completely out of it that together make that effect?
That's a good question. Basically, they go out of sync.
Okay.
You can only tell there's a planet there if there's something periodic,
Okay.
like a sort of metronomic tick in the signal. If it's two, they're not going to add up every orbit, so it'll be like Yeah, it'll be like some weird thing. Okay, practicing my drumming. Okay, so not 0.2, what do I say, miles per hour, really, really slow. I asked Google to compare it to some animal, and I found a sloth, specifically when threatened.
Yes.
A threatened sloth is an interesting thought. So this sloth going towards you would be a little bit bluer, but you can imagine at speeds much like this, it wouldn't get significantly bluer. And that is really the issue when it comes to finding Earth-like planets with this method, that you need a really, really good detector to see sloths on the sun. I never thought I'd say that. But really the biggest issue is, remember the eclipse, where you could see all the stuff coming off the sun? Well, if you're trying to see the sun move towards you, but its surface is broiling and bubbling, then that's noise in your telescope. All your telescope sees is this like random chaotic jumble from the surface of the sun, and the sloth is completely evaporated and lost in the data. So the future of planet hunting is really to try to find a way to remove not just the light of the star, but the variability of the star as well. It's still an unsolved problem. Maybe some of the students' generation will solve it, but we will see. So arguably, there's the thought again, arguably the most successful, I'll just check the time because I think that clock's getting a lot. Arguably the most successful way of finding planets is whenever you get lucky and you're looking at the star and the planet comes across the front. This is called transiting. Okay? And the idea would be that you have your trusty flashlight, and if you have a planet, you'll get lucky and it'll move in front of the star. If that happens once, you probably have some blip in your telescope. But if it happens again, and again, and again, and again, in a periodic way, you probably find yourself a planet. And if it happens once a year, around a star, much like the sun, you probably find a planet that has a similar orbit to the Earth, and therefore is potentially habitable. And the telescope tasked with determining how many stars have such a planet that transits, use the word, once a year, was the Kepler spacecraft, which was launched in 2009, and unfortunately started kind of dying in 2013, but finally bit the dust in 2018. And the Kepler Space Telescope stared at a patch of sky that's roughly the same as your thumb at arm's length, and looked at about 250,000 stars in that, and just watched. Just stood there, very, very patient, watched them, and looked at the light from all of the stars to try to see if any of them had this metronomic tick. And it found thousands, essentially. Thousands and thousands of planets, and I will just throw up some, this is my only graph here. I will show on the horizontal axis here the orbital distance of planets. So this is 1 times the Earth's distance. This is 0.1 times the Earth's distance. Mercury in our solar system would be somewhere here. And there's a reason I'm leaving all of this space where we have no planets open. And on the horizontal axis, we have the physical size. So like that would be the tennis ball versus the chia seed of the planet in terms of Earth, Neptune, and Jupiter. And roughly the distribution of planets, Kepler found, had this huge mass of planets that are ridiculously close to the sun. This is 0.1. This is 10 times closer to the sun, to their star, than the Earth is. And they're the size of Jupiter. So they're hot, and they're the size of Jupiter. And if you spend any time with astronomers, you know they're super creative. So they call it hot Jupiter. Ones that are a little further out, they call warm Jupiters. And I've even seen a paper proposing the idea of tropical Jupiters. That one didn't stick, thank God. All right. So those are common. They look common, but it's because they're easy to find. They're not actually that common, even though they take up a large bulk of the data. But what's really common is this bunch down here. These are planets that are closer to their star than Mercury, so they're really hot. But they're a little bit bigger than Earth, but not quite Neptune. And these are the most common planet that we know of, and probably the most common planet that exists. And they're called super Earths, again, the naming tradition, or people argue between super Earth and sub Neptune. I don't have a hat and ring, but they're somewhere between here, which is interesting because it means the most common type of planet is not represented in our solar system. So there's something a little bit weird about this. Okay. And just one of my favorite examples of these, they're really close in, is this one, Coro 7b. I'm not sure that's actually in the same data set, but this is a good representation of some of these really close-in planets. If you calculate how hot its surface is, it's 1,300 degrees Celsius, which, if you look up lava, is chilly compared to that, 1,200 Celsius. These have been called lava planets, and I had to make a Star Wars reference just because the kids don't get any Star Wars references. So this is definitely not habitable. And the problem with the transit method is that it's very good at finding close-in planets, but it's not very good at finding planets that are at Earth's distance. The entire Kepler mission, even though it found thousands of planets, only found a handful that are in the habitable zone, and it only found one that was in the habitable zone of a star that's kind of like the Earth. G stars are the Earth's type. These ones are the small ones. Small ones could still have life. It's just if we really want to find Earth 2.0, we want to find planets around stars. And I did have more, but maybe that's a good place to kind of wrap it up. So Kepler, the most successful, found one planet that you could really call Earth 2.0. The thing is, a lot of you could probably guess that if you're dealing with transits, you miss a lot because you only see planets that go in front of the star. You don't see ones that do this. So whenever that uncertainty is patched in and you say, okay, we find this many, how many did we miss? Astronomers have this thing that they call eta Earth, which is basically the fraction of stars that have an Earth-like planet in the habitable zone. Okay. They find that the number, though uncertain, because we only find a handful, is between 30% and 60%, plus or minus big error bars. But regardless of the error bars, the conclusion of the Kepler mission was that roughly maybe 1 in every 2 stars has a planet in the habitable zone, which is a pretty good result.